So this is the first lecture of this series of support vector machines. Okay, in this lecture we will learn about the geometric intuitions behind the support vector machines. So okay, let's start. So the main thing of support vector machine is that it is a simply classification as well as regression technique, and it is also a popular machine learning techniques for classifications. In early 90s, this, this algorithm is very popular. So let's start about this algorithm. So this SVM is the most popular machine learning algorithm, and it's mainly used in classifications as well as regression techniques. Classifications as well as regression techniques. Okay, and in 1990s, in about 1990s, this algorithm is mostly popular classification machine learning algorithm. So the geometric intuitions, now the geometric intuitions is behind that. So suppose before going to the geometric intuition, first let's draw a picture. Okay, so let our positive point, first draw the positive point. Suppose we are drawing here positive power in blue ink. This is our positive point, and using the pink, suppose using this red ink, we are using the negative point. Suppose this is our negative point. And in this, just I am redraw this point more clear. It will be more understandable if we take this point like that. Okay, so you see there have many planes that separates the 2 points, that two classes. Okay, but we have to choose the best one. In logistic regressions also we learn how to choose best plane. So similarly here we have to choose, in this technique also we have to choose the best plane that separates that. So the technique is such that, so simply we see that here blessed planes that separate these two things is that is the best plane. But here also have another plane, else maybe you can see that it is also another plane that separates that one, and here maybe this plane that separate also, here maybe this plane that separate this one. Suppose let this one. Okay, this one that's also separate for two data points, but among this plane we have to choose the best one. So let's this plane is our pi 1. Let this is our pi 1 plane, and its normal vector of this plane, it's called, let its normal vector of this plane is w1. So now the question is how to choose the best plane that separate our data point from positive to negative. So just write the thing. So there have some pi's, there have many pi's, there have many pi's Many pies means there are many planes that separate the positive from negative. Okay, and the key idea is that, so we have to choose the pie such a way that separate widely as possible edge. Means that we have to choose that pie. We have to choose that plane that separate our positive and negative point as widely as possible. Means what? Means we have to choose such a plane that separates and positive and negative point as widely. So wild distance is what? It's closer negative point is what? Suppose if we call this point is positive point and this point we call that it is a negative point. So the closer point of this plane is what? This one, and closer point of this plane from negative side. Now negative point is what? I think it will be this one. Because it will be this one. So if we just taking the perpendicular from point and perpendicular from this point, so the distance, the sum of this distance is the spread of this point. Just write it. Just I think draw another plane parallel to this. So the plane that is parallel to this point that touches our positive point is this one, and the plane that touches the negative point that is parallel to our base point is this one. Now the distance of this point is from that plane is what? This one. This is the separating distance. So simple, this was the separating distance. This we call the separate distance. This distance is called the oil distance. Now in SBIM, main key ideas is that we try to maximize this distance, that is right in pink ink. Just see the pink ink, pink color. Just the pink color plane. Just see this plane, this line. We want to maximize this distance. Okay, so just write down. So the key idea of SBM is that we have to choose the pie that separates positive points from the negative points as widely as possible. Okay, this is the main key idea. Everything else is the same, just this is the key idea of SBM. Okay, one thing is that if you just remember the logistic regressions, so in logistic regressions we see that the point that is far distance from our plane, the probability to lie on this region is so high, and that point is closer to this plane and lie on this region is so low, that is near about 0.5. So just take this point. So this point, so this point is far away from the suppose if we take the separator line, suppose let's take this red line is the separator from positive to negative point. If this point is the far away from our plane, this point is the far away from our plane, And if we consider this point, this is the closer than the than that points, this point is the closer than that points. So the probability of this point to lie on the positive region is high. So let's its probability is 0.9, but its point to lie in the positive region, its probability is 0.55. It's about that. Similarly for negative point also. Okay, just we have learned this concept in probably in a logistic regressions. And if you just remember the probabilistic intuitions of the logistic regression or just of the logistic regressions, then we have read this concept. Okay, so how we can think this concept by using simple sigmoidal functions. So sigmoidal function, if you just write this concept in probability of yi of class 1 is we think as this concept by this w transpose xi. By simple using this formula we are just see this thing. So the far away points from our point, the probability is to lie on this region will be high and closer of this point. So simple using this formula. Just if you forget this, I request you please go to the probabilistic intuitions of the logistic regressions and easily you can find. And there, sorry. Now the come to the another geometric part. How we can calculate it the widely as possible, as we can wide the this distance. Okay, so let's redraw again this picture. So let's our positive point is this. Okay, and the negative point is this. I am taking the red color for negative points. Okay, so this. Now here we have to find the base separator. So let our separator is like this is our separator. Okay, and the separator parallel to the separator, this is our plane. Let's call this plane is pi. And the perpendicular of this plane is called the w. This plane is the w. Okay, this is the perpendicular to our plane. Now just we are draw a plane that is parallel to the plane. We are trying to draw the plane that is parallel to the plane and touches our positive point. Okay, let's take another color. We're taking the white color and now draw a plane, another plane that's parallel to the plane. Simple, just to draw this and touches our positive point. This is the parallel of the plane and touches the positive point. So which point it is touches? This point, this point, this point. Let's take this point. These 2 points, this our plane is touches. Okay. So this point that is parallel to this plane and touches the positive point, this plane is called the pi plus. Let's each call the pi plus. And another we are redraw one plane that touches our negative point and parallel to the our plane pi. Let's this one. Let's this pink one. This plane called the pi minus, and the touches point, what this point is the touches to our negative plane, this point. and here these 2 points are, and the distance of this point. Suppose this point is the distance, this is the distance between these 2 points, just green line. See the green line. These are the distance of the point pi plus and pi. This is the distance of the pi plus to the pi minus. Okay, this distance, let this distance is d. Here's this distance is d. This distance is called the margin. Okay, this distance is the margin. And our main motto in this SVM is that we have to maximize this d for every plane. If we have another plane like this, then also corresponding this plane we can draw pi plus and pi minus also using the same methods, and then in that plane we can also easily calculate it, the distance, that is margin of that plane. So our main motto among all the plane, we have to maximize that this d. This is the main idea of the support vector machine. Okay, so here pi plus, just to again rewrite it. So here pi plus is parallel to pi, and here pi minus is parallel to pi. Just I'm write this thing. Now if you think, just think another plane. Just I am using another color here. Suppose I am using this one, this green. Just I am now just simply draw another. Just I am using the bold. Okay, just see this point, that is the using deep green color. Here I am using this plane. If you simply find that margin of this according to this plane, so here by this from this plane, if you call it the, if you called here, it is the pi dash. For this plane, pi dash plus is where? Pi dash plus pi dash plus are passing through this that line. Using that line, this is our pi dash plus, and the simple the pi dash minus also passing through this point. This is the negative point, this is our pi dash minus. So the separator among this point is this. If we call this separator d dash, so simply d is greater than d dash. So d is simply greater than d dash. Our main motto is have to find, we have to find maximum d, max d among all the d's. Okay, we have to find that. Let's call, we have to find d star, that is of arc mean of some functions, that is margin function. Let call this is the margin among all the d. So it is one will be max. Okay, simply this is the main motto of our logistic regressions. So in another language, if we compare these two things here, using another color. Here I am using another color. So pi here, pi, the plane pi is more better than our pi dash plane, and the pi This is a more better because why this plane is better? Because the D, that is because margin of pi is maximum among all other pi's, among all other pi's. Pi dash, all other pi's means pi dash, all other pi dashes. Okay, here pi is the maximum. Okay. So simple, if we just read, I think the main objective of our, so the main objective of our SVM, just using this thing, this picture, and we got the main objective is our, we have tried to find, we are trying to find a pi that maximizes the margin, that maximizes our margin, means this distance, that maximizes this distance. So margin means distance of our pi plus and pi minus. Okay, so if our, simply here you can see, if our margin increases, here if our margin increases, then our accuracy increases. Just simply, if you think as logistic, just compare this thing in logistic regressions, we see that the point as closer and closer to the plane, the probability is, the probability of that point to belonging this class will reduce. Here we are trying to maximize this distance, so that will increase our probability that this point, chances that increases that to lie on that region, probability that that chances will increase of that point that will lie on this region. If it is closer and closer to this point, then probability is decreased by simply using this formula. So simply we are trying to increase this distance, positive as well as from negative. Okay, this is the main, this is the two different interpretations, but our motto is same. Okay, so if we write this is simply, if we just increase our margin, that implies if our generalization accuracy is increased. Okay? Our generalization accuracy is increased. Simply, if we increased our margin, then our generalization accuracy will increase. Now come to the support vectors. Why this theorem is called support vector machine? So first, before calling this theorem, because before this calling the algorithm support vector machines, so first you have to understand what is the support vectors of this algorithm. Okay, what is support vector? Let's come to the concept of support vector. So again, just rewrite. Suppose this is our positive point, and the red color, suppose this is our negative. And the plane that separate using the maximum margin, that separate both the plane that I am taking here, that uses the maximum margin. Okay, this plane. Yeah? Taking the positive plus, if you just step for positive point, I am, that is the pi plus, it will be our pi plus, and this point, this plane will be our pi minus. This point, this plane is our pi minus. This is the pi minus, and this is the pi plus, this is the pi. Okay, and this distance is the marginal distance, is the d, that is equal marginal distance. So here support vector machines, that is the points, the point that touches the vectors, means this point that touches our support vector planes. That is support planes means what? That is positive, pi plus and pi minus, the support vector planes. And these vectors here, these vectors only touches our pi plus, and here only these vector are touches our pi minus. So these 2 points are called the support vectors. Simple, just write down. So the points to which our pi plus and pi minus passes are called the SVS, means support vectors, to which pi plus and pi minus passes called SV, support vectors. Okay, these points here, these points and these points are called the support vectors. Because this reason, because this is the most important vectors, this is the mode in the SBM, in the whole SBM, in the whole SBM, these points are the most important point. So because of this, we call this algorithm the support vector machine. Okay? So using this name, you are already learned how important these vectors are. So it is so important for vector support vector machines. So we rename this algorithm as support vectors. Using the support vectors, we rename this algorithm support vectors machine. Because of this, now I'm coming to the another geometrical. So I think these geometrical intuitions, why the support vectors machines, how it works, and what is the geometric intuitions behind it, I think all of you clear. Now I'm coming to the another geometric interpretation of the SVM. Okay, another geometric interpretations of SVM. Another one, or you can call it alternative. Okay, and alternative geometric interpretations of SVM. Maximum authors and books are using this general technique. First I am discussing it. You can easily find this technique in some blogs. They are using this technique. Okay, this is also very important concept. So before discussing these interpretations, we have to discuss about the convex hull. What is convex hull? What is convex hull? So first discuss it. Suppose let's take, we have some data points like that. We have some data points like that. So convex is that we have to connect these data points in such a way that that creates a convex structure. That creates a, suppose here how we connect it, here we can connect it this, this. If we connected this thing, these points, so this structure will create a convex structure. So because of this structure is called convex structure, and this thing is called convex polygon. This thing is called a convex polygon because this structure is a polygon structure and it is also a convex structure. So this thing is called a convex polygon. We have to create a convex polygon to joining the points such a way that this is a convex polygon. So if we another, so simple, the smallest convex polygon is what? This is a triangle. Simple. This is the smallest convex polygons. This is the smallest polygon. And sir, what is non-convex polygon? If you ask, the non-convex polygon structure is like that. If you just simple create this structure, suppose our data points is here, one is here, one here. If we just connect this point, we have just simply connect this point. Here, this structure is not a, because if we just join these 2 points, so these 2 points, so this distance totally outside of our polygon. Okay, so this structure is a not, this structure is not convex polygon. Okay, but if we join this structure in such a way like that, if we just I'm thinking just such in just follow our thinking, I am just going to join this structure in such a way. Okay, then this structure creates a convex polygon. But if we join these things, so it is not a convex structure. Is a polygon. Okay, so just follow the pink ink. This creates the convex polygon, and the green ink that is here, that is this green ink, it is not create a convex polygon. So this is the simple concept of convexity. Now using this thing, now using this concept, I am coming to the concept of SVM. How the polygon creates SVM. So first, so I think geometrically visualize the thing and understand is so easy. Geometrically, the human mind is created in such a way that it's understand very easily in geometrically. Okay, so suppose we take our positive point blue ink and a negative point red ink. Just create it first using the blue ink. I'm creating the positive point. Suppose let this one. This is our positive point, and rating I am using for okay. So this is our positive point and this is our negative points. Now we have to create a convex hull using the, so to create I'm using the red white ink. Suppose I'm joining this point, this point, this point, this point, this point, and this point. So I'm just joining this point to create a convex hull. Simply using this, just join between any two of this point. So the distance is lies on this polygon. Okay. Similarly, I am using here this distance to join this polygon. Just see the white ink. So just I am joining this point to create this polygon. Now the main concept of the polygon is that we have to find the 2 points. We have to find, just see the edge of this polygon, and we have to, in the edge, we have to find these 2 points that are closer to each other. Okay, here if you see, just here exit point is what, just I am using the yellow ink to denote the exit point. Here it is our exit point, here is exit point, here is exit point, here, here, and here, and here. This is the exit point of the positive polygon, and the exit point of negative polygon is what, that is negative, this point, or the exit point of this negative polygon. And what among these point, which of the 2 point are closest? These are the 2 point at the closest point. These 2 point, these 2 points are the closest point of this. Okay, these 2 points are the closest point. Now the we have the main, the first just write down this concept algorithmically. So first just okay. So first I am what? First I am creating the positive convex hull for positive points and negative points. First we have what doing? First we have creating a convex hull for positive points and negative. Number one. Number two, what we are finding the shortest line connecting these hulls. Okay, so here shortest line is this one that connecting these two hulls. So first, then in next step we are find the shortest line that is connecting these hulls. Okay, here this one. First, just this one, then marking this one. The in third step, what? Bisect. Now in third step we have to bisect this line to create our optimal plane. So how? Here I am just using the, now we are just going to bisect this. Simple, the bisect, and the plane will be parallel to the bisector, perpendicular to the bisector. This plane is our called the optimal plane. This is the simple concept. This is called our optimal. It's called pi. It's a margin. In just if you see this concept, just you compare this concept of above concept, these both the plane are the same plane. Here I am using the convex concept here, and here we are using the marginal concept, but both the plane are the same. So in third we are calculating bisect the line. Okay, part we have bicep this create. Okay, this is the second. Okay, I think these geometrical interpretations, both the geometrical interpretations are clear all of you. What is the geometrical intuitions, and how is the main motto of our support vector machines? I think all of you are clear. So if you have any problem, comment below, and in next lecture I'm coming to the mathematical formulations of SPM. Okay.